Hello, 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 hello. Today is May 3rd, 2019. I recorded the solutions to problem 61, probably more than 6 weeks ago. And you will see that solution. It's coming up right now. However, I decided to not only do the fast, wonderful, great solution, but to do it also in the more classical way by simply write down the equations of the conservation of momentum and the conservation of kinetic energy, and then come to the same conclusion. So you will see that at the very end. And the reason why I decided to add that is that some of you probably, many of you probably tried to solve that way. They tried to solve it by really going back to the basic Newtonian equations rather than the fast solution, in which case I transfer to the reference frame of the basketball. All right? So hang on. You will see then a beautiful solution, the mother of all solutions, and then you will see the way that probably most high school students will do it. And of course the answer will be the same. Hello, 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 hello. I'm going to discuss with you the solution, or a good approximation of the solution. When we have a tennis ball on top of a basketball, we drop them from a distance to the floor h, and if all collisions are elastic, when the basketball hits the floor at a certain speed, it comes up from the floor with the same speed because elastic collision, so it comes back to the same place where it was before. It comes back to a height h above the floor. Yet, if you now look at what the tennis ball is doing, it will fly way higher than h before it comes to a halt. And the question now is, how much higher? We're going to make some simplifying assumptions. One is that all kinds of collisions are elastic, so there's no kinetic energy lost. The mass of the basketball is much, much larger than the mass of the tennis ball. So we drop them from this height, and so the basketball hits the floor with this speed. This is of course trivial. You should remember from your high school, mgh is 1/2 mv squared. Gravitational potential energy is converted to kinetic energy. So the speed with which the basketball hits the floor is 2gh. Square root of 2gh. Now I'm going to consider the following. I'm going to consider, which is of course a simplifying assumption, that when the basketball comes up, that the tennis ball is coming down. The simplification of the problems. But you get a very accurate answer actually. So now we assume that the tennis ball is coming down with this speed on top of the basketball, which is going up with this speed. So you now have a tennis ball coming down with this speed and a basketball coming up with this speed. And this collision I'm going to consider now as an elastic collision. Let's move to the frame of the basketball. So we are sitting on the basketball. So our speed is now 0. But now of course the tennis ball is now coming down on us with the speed 2 times that. 0 for the basketball, 2v for the tennis ball. So in the frame of the basketball, since the basketball has a way larger mass than the tennis ball, the tennis ball will bounce off the basketball with exactly the same speed at which it came in. It came in with speed 2v, so it will bounce back up with speed 2v. So, the tennis ball will bounce up with speed 2v in the frame of reference of the basketball. Now we go back to the laboratory frame. I call my lecture hall the laboratory frame. And so we know that in reality, in my frame of the laboratory, the basketball is going up with speed v. But we also know that relative to the basketball, the tennis ball is going up with speed 2v. So the net result is that in my laboratory frame, the tennis ball will go up with speed 3v. Well, if the speed is 3 times larger than this value, the only way that can happen is that h must be 9 times larger. So the tennis ball comes to a halt at a height which is 9 times larger than the height at which the basketball will come to a halt. Now, when you do this experiment, you're not going to find a factor of 9 for a variety of reasons. The most important is, of course, that your assumptions that the collisions are perfectly elastic are not correct. But don't be surprised if the tennis ball goes 6 or 7 times higher than the height of the basketball. So give it a shot. And the answer that I was expecting from you with all these simplifications is that the tennis ball bounces up 9 times higher than the basketball. Okay? It's a very impressive demonstration. You can do that at home. Of course, the floor on which you have to do it must be tiles, hard tiles. You can do it outside maybe. And it's really impressive to drop that basketball. Don't drop it from 1 meter high. Drop it from a little higher. And if you think about it, why I do that, you'll probably come up with a reason. Don't do it from 1 meter, but do it preferably from 3 or 4 meters high. And then whoosh, it bounces and whoosh, goes the tennis ball. All right then. Have a nice day, take care, and do this experiment and tell me how it went. So just tell me that. I'd be very curious. Hello, 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 hello. So today is May 3rd. And I'm going to add to my super solution, which you have just seen, I'm going to add the poor man's solution. But it doesn't mean that those of you who did it this way are poor, of course not. But the reason why I call it the poor man's solution is it's so much more complicated. And it's so much easier to make algebraic slips. So that's the only reason why I called it the poor man's solution. So don't take it personal in any way. So are you ready? The problem is a one-dimensional problem of an elastic collision. And we discussed the moment that the basketball is just coming up after it bounces off the ground, and that the tennis ball is still falling down. They have both about the same speed, as you will see, because the tennis ball comes down falling over a distance h. The basketball fell over a distance h, bounces off the floor and comes back up again, with approximately the same speed that it came down. Okay. So, we are discussing the moment that the basketball is coming up and that the tennis ball is coming down. I will now forget about the basketball and the tennis ball. I will derive in the most general way elastic collision of two objects, one-dimensional. You want to think of them as horizontal, that's fine. And I will write down the conservation of momentum at the moment of the collision, and because it's an elastic collision, the conservation of kinetic energy at the moment of the collision. I have an object M1 which is moving with velocity V1 initial, that is just before the collision. I have an object M2 which is moving with velocity V2, I stands just before the collision, that's initial, the I. After the collision, M1 is moving with velocity V1F, which means final, and M2 is moving with velocity V2F, which means final. Here comes the conservation of momentum. This is the momentum before the impact, notice the I's. This is the momentum after the impact, notice the F's. I put here arrows to remind you that it is of course a vector equation. Conservation of kinetic energy is not a vector notation. So these are vectors, but in what follows I will remove the vector notation. Of course, I will have to be careful that at the very end I will have to remember that the velocity of the basketball when it is going up is in the opposite direction of the tennis ball when it's going down. So I don't worry about that now, but trust me, at the end I will not overlook that. So I prefer to keep all those plus signs for now and only make the correction at the very end. So, conservation of kinetic energy is then pretty trivial. You can confirm that this is the kinetic energy just before the collision, and this is the kinetic energy after the collision. Now you have to combine these two to find the velocity of the tennis ball after the collision. What a headache! What a headache to combine this one with this one. I will not grind you through the details of the math, but I will tell you that if you do your homework, if you spend enough time on it, you can demonstrate that V1F is this. So I now have mass ratios here, and I have the velocity of 1 initially and the velocity V2 initially. If this is correct, it's easy for me to write down now what the velocity of number 2 is after the collision. Because all I have to do is replace this M1 by M2, this M2 by M1, this V1 by V2, and this V2 by V1. And I did that. M1 minus M2 is now M2 minus M1. M1 plus M2 is now M2 plus M1. V1I is now V2I. 2M2 is now TM1, 2M1. M1 plus M2 is now M2 plus M1, and V2I is now V1I. So if this is correct, this must also be correct, because there's nothing special about M1 and M2. Now comes a key moment. Since M1 in our case is much larger than M2, look now at this equation. If M1 is much larger than M2, then this is 1. And so V1F is then V1I, V1F is V1I, If M1 is much larger than M2, this is 0. So this is the result from this. If M1 is much larger than M2, this is minus 1. So I get here minus 1 times V2I. Minus 1 times V2I. Minus V2I. If M1 is much larger than M2, this is 2V1I. So I get 2V1I minus V2I. Now comes the moment that I have to recognize that V1I, when the basketball comes up, is in magnitude indeed the same as V2I, but they have opposite signs. And that has to be taken into account, of course. In other words, V1I is minus V2I. So minus V2I here is also V1I. So V2F is now 3V1I. But V1F is approximately V1I. That's obvious, by the way. It's obvious this basketball is so massive that when it bounces off the floor in an elastic collision, it obviously comes back up with about the same speed as which it came down. That teeny weeny little tennis ball can be completely ignored to a first and second order approximation. And so this V1I is also V1F. And so now you see that the speed of the tennis ball, which in my case is V2, is 3 times the speed of the basketball when it comes up. And therefore, the tennis ball will go 9 times higher. Okay, so for those of you who did it this way, I totally understand that. I completely respect that. It's a nightmare. It's a lot of grinding. It is a lot of math. But it's perfectly okay. I prefer the solution that I did first, which I would call the mother of all solutions. Okay? Take good care of yourself. Have a nice day. And try to be friends with me, because I would like that. Yes, I would really like that.